Hello everyone, welcome back. Hope you had a great Diwali. In this video, we'll be discussing about the last problem of this week's weekly contest, maximum strong pair XOR 2. The problem is very interesting and I would say is a very well balanced hard level problem. The problem shares one similar concept from the last week's third problem itself. I already have a detailed video for the last week's third problem in the channel. If you have watched this video, I would encourage you to pause the current video and give the current problem maximum strong pairs or to a try by yourself. If you haven't watched last week's video, I would encourage you to continue with this video, and we will you can solve the other problem, last week's problem, by yourself as a follow-up. So with that, let's get started. The problem states that you are given a zero indexed array nums. A pair of integers is called strong if it satisfies the following condition. The condition is modulus of x minus y should be less than equals to min of x comma y. Now you can select two integers from nums such that they form a strong pair, and their bitwise XOR is maximum among all the pairs in the array. So you are given array nums. In this array nums, you can select pairs of number, and some pairs of number will be a strong pair. Among all the strong pairs, you need to return the one which has the maximum bitwise XOR, and you return that as an answer. So let's take an example. Let's say the array is 1 2 3 4 5. Now in this array there are 11 strong pairs. These are the 11 strong pairs. So notice each of these pairs satisfy this criteria, that's why they are strong. So let's take 2 comma 3. Modulus of x minus y, which is 2 minus 3, is 1, and minimum of x comma y, which is minimum of 2 comma 3, is 2. 1 is less than equals to 2, which is a correct inequality, and hence 2 comma 3 is a strong pair. Similarly, all these pairs are strong pairs. Now among all these strong pairs, for bitwise XOR of 3 comma 4 is the maximum, and hence 7 is the answer, which is the bitwise XOR of 3 comma 4. So hope the problem statement is clear. Now how to solve this? As always, let's try to drop certain constraints in the problem to make it simple, and once we solve the simpler problem, we will get back to the original problem after that. So in this problem we have two main criteria. First, we need to select two integers such that they form a strong pair, and we also need to make sure that the selected pair has the maximum bitwise XOR. So bitwise XOR is a slightly tricky operator. So let's try to reduce this to sum, because we all know how summation works, and it's different properties as well. So the reduced problem now is we have to figure out the strong pair. Again, definition of strong pair is still the same. We have to figure out the strong pair which has the maximum value of x plus y, right? So what is the brute force solution of this problem? Simple, just try out every possible value of x and y, see which of them are strong, and if they are strong, just see among all of them which has the maximum value of x comma y. So the approach would be, you will start with every pair. So you will say, okay, this is my L, or this is my x, and I will try out every possible y for this particular x. So I will say this is my y, this is the y, this can be y. For each of these I will first evaluate whether the pair is a strong pair or not. If it is a strong pair, I will select these and keep it as one of the validated candidates in our result, and figure out the max over all of them, and that will be the answer. Now what is the time complexity of this entire solution? simply order n square because we are iterating over all the pairs, right? So this, for this x we'll try out all the y, for again then we will increment our x, and then we will again try out all the y. So that way it is order n square. Now surely this will not pass because value of n is 5 into 10 to the power 4, so we need to reduce this. Now how to reduce this? Where from two n's are coming from? We had two n's, right? N cross n. So this first n is coming from the fact that we are iterating over all the x, right? And second n is coming from the fact that for each x we are iterating over all the y's, right? So if we need to reduce this complexity, like one of these n, that indirectly means that we can't afford to iterate over all the indexes of the array, right, for each x. So which in turn means that this expression we don't have the liberty to evaluate this expression for all x and y. So what we can do is we have to actually separate x and y from this expression, because if x and y both are there in each side of the expression, it is impossible to evaluate this expression beforehand. In other words, you can't say for this particular x what are the probable values of y, or what is the range of values of y. You can't say this until you have both x and y in both LHS and RHS. So let's try to reduce that first. So okay, I'm not sure why it is reversed, but let's forget about this. So let's assume that x is greater than y, right? It can be the other way around as well. Y can be greater than equals to x as well, but one should be greater than the other, right? For sure. So let's assume that y is greater than x, greater than equals to x. Now what is the value of mod of x minus y? X is smaller, right? So x minus y would come as negative. So actual value we will just do minus. So the actual value of mod of x minus y is y minus x, right? This should be less than equals to min of x and y. Now what is min of x and y? It is x, right? So in other words, y should be less than equals to 2x, right? So if x is 5, we know that y should be less than equals to 10. And remember, our assumption was itself y is greater than equals to x, so y should be greater than equals to 5 as well. So y should lie between 5 and 10. Now once you have this range, notice that you can simply go in the array and figure out which element in between 5 and 10 is present in the array, and you can simply pick that, right? So let's just sort the array, because we have seen that this is lying, y is now lying in a range, and if the array is sorted, we know that it is easier to work with a sorted array for range solutions, right? So let's keep this with us. Now we just sorted the array. Let's say this is x. Now for this x, we know y can anywhere between 2 and 4. So in other words, y should be lying in this range L comma R, right? What you want to find? You want to find out the maximum value of x plus y. So you already know x is 2. Now in one pair, like y can be this or y can be this, only two choices are there. Now for when y is this, the value of x plus y is 2 plus 2. When y is this, the value of x plus y is 2 plus 4. Among these two, we are always certain that the second one is the maximum, because whatever comes last is the largest value because our array is sorted. So what you can simply say, I will simply go and figure out the nearest value from 2x, and whatever is the nearest value from 2x is, that will be my best y for this particular x, and I will do it for all the x, and that will be my answer. So let's just take one complete example. Let's say this is the array. We are trying to find out the same thing, maximum value of x plus y. So what we will do, we will first start with this particular x equals to 0, or index of x is 0, so x is 2. Now we know if x is 2, y can be anywhere between 2 and 4, right? So we will just do a binary search over the array and see which is the nearest value to 4. In this case 4 itself is the nearest value. So we know that 4 will be the one which will give the maximum value with this particular x. So our current answer, or basically all the strong pair for which x is this, among all such pair, the maximum value of x plus y is 6, right? Now let's try out other x as well. So now let's see if x is this. If x is this, again y can be anywhere between 4 and 8 now, right? So y can be anywhere between this index and this index. Now among this index, we know that this one will be the one which will give us the best result with x plus y. So with this particular x, the best possible y is this particular index, which is 4 plus 8, 12. So we wanted to find the maximum value overall. So now previously for this x we got the maximum value as 6. Now for this x we are getting maximum value as 12. So let's just replace it with 12. So this is the final result that we have, right? So this is our answer. Now similarly we will try out the next x. For this x, again we know that the y should be anywhere between 5 and 10 now. So y can lie between this range and this range. So in this case again we'll take from this 5 this 9, and it will come as 14. So we'll update our answer because 12 is smaller than 14, so we'll do 14. We'll keep on doing this for all the value of x, and finally we'll have our maximum value of x plus y across all the strong pairs. Now what is the time complexity? For each, what we are doing, for each x we are iterating over, we are first finding out what is the range of y. That just takes order one time. After we figure out the range of y, we figure out what is the closest value in the array with the largest value of y, and that we will do via binary search. So for each x we are doing a binary search over the entire array, and that will take logN time, and we are doing it for all the elements. So overall it will take order n logN time, which is obviously a lot better than order n square, and which will pass the given time constraint as well. But here the problem, first of all, the problem is not addition, it is XOR. And second, what if I say that you can optimize this n logN to order n as well? So if you are following this channel again, I would strongly encourage you to pause and try to reduce this n logN solution by yourself to order n. Just to reiterate, the order n logN solution looks something like this. So what we are doing for each L, we are trying to find the value of R, or in other words, what is the range in which we will be trying to find out the y. Now for this we want maximum in the range L comma R, which by definition will be the value at R. So this entire thing will turns out to be array of R. So we'll just add array of L plus array of R, and we will keep on doing this for all the L, and across everything we'll keep on accumulating the maximum, and that will be our answer. Now we need to optimize this further. So notice we have to remove this login. From where this login is coming from? Because we wanted to find out the best possible R, or what is the range in which there can be a valid Y. So think about it. For this L, you are trying to find out the best R using binary search. So let's say you find out the best R, which is in this case is this. Now once you have the best R, so let's just get rid of this for clarity, right? So once you have the best R with you, what will you do? You will increase L. Now for this L, again you are trying to find all best R across the array, right? So this is the place from where this login factor was coming from, because you are trying to find R all over again. So we need to somehow skip this. We don't need to, or we can't afford searching for R across the entire array every time. So what is the approach you will take in this sense? In this criteria, you will see whether R follows some characteristics. If it follows some characteristics, then only it is possible to do so, otherwise it is not, right? So in this case, R does follow increasing characteristic. In other words, for this L, you find out this is the R. Now when L is this, will you imagine R going backward anytime? For this L, R should always be greater than what it was there previously. So previously R was this, now R can be somewhere around here. It can never go back. Why? Because L is going rightwards. In other words, L is increasing. So if L is increasing, X is increasing, right? And we already know the value of Y is in between X and 2X. So if X is increasing, the minimum value of Y is also increasing, and so does the maximum value of Y. So because minimum value itself is increasing, you can't R can't be less than L for sure. So R will be after L. Now whatever R was there for previous L, that R will go much forward, because now you have more bandwidth to go right. So for example, for when this was the L, this is the R, right? Because X is 4, so Y can be also 2, 8. So this is the R. Now when L comes here, it is certain that R can't be any of these. Why? Because L is increased, right? X is increased, which means 2X is increased. So you want something which is closest to 2X. So this R was closest to previous X, which is 2X minus 2. So something closer to 2X will always be greater than 2X minus 2 if it exists. Otherwise it will be the same, right? So R is always going right. So for each L, whenever you are increasing L, R has the potential to increase, but R will never decrease. So in other words, R starts from somewhere here and go all the way up to the last index, and so does L. So overall we are just iterating over the array twice, and the overall complexity is reduced to order n, right? So just to reiterate, we are able to apply this two-pointer approach because the given problem or the given inequality satisfies the criteria that R has a increasing nature, or in other case it can be decreasing nature as well, but R has a strict nature, either increasing or decreasing, and hence R is not fluctuating between left and right, which in turn will say that R we will be iterating over the array, searching for r in just one direction, and hence r will just go over the entire array once, and the complexity will be order n. So the pseudocode for SEM would look like this. Just compare it with the previous pseudocode. So let's just get rid of all of these. So pseudocode would look something like this. What we are doing, for each L, we are trying to find out the best R. So for each L, we are trying to find out which one, if R can go right. If R can go right, we'll make it go right, and we'll consider that element into our current working set. And once we have all the R's that is possible in the current range, we will simply take the maximum among all of them, or in other words maximum across this elements array, right? Or elements data structure, whatever it is, either an array or a set or map, whatever it is. You'll just do a, you want to find just the maximum in the range elements, maximum in the elements data structure. Whichever is the maximum, you will just add it with the array L, and that will give you the maximum value of x plus y for a given value of x. And finally, because you are moving L to the right, you will be moving L to the right, the previous L is no longer a valid candidate, right? So we'll simply remove it from our set as well. So this is the overall algorithm for maximizing x plus y. But the original problem was how to maximize x XOR y, not x plus y. So I would strongly encourage you to pause and try to solve the original problem now by yourself. That is, instead of maximizing x plus y, we now have to maximize x XOR y. So hope you have at least given a thought to it. The solution will be exactly same. What we were doing, we were simply iterating over the array from left to right, and in each iteration we were simply taking care of the right value of r, right? So we started with r minus 1, and for each L we just incremented r to until it can, and finally we figure out the result by doing a max across previous result and the current result, and we then remove the current element. So only difference now is, we, instead of finding out the sum which we know that across elements the sum would be the one which have the maximum value, we now need to find out the maximum XOR. So we have a bunch of elements, right, with us. So this elements array contains only the element that is valid for a given x. So we have a bunch of elements, right, and we have a number, let's say x. With this x, we want to know which one of these elements will give the maximum value of XOR, right? So each of these has some value of XOR with x. We want to know which one will give us the maximum value. Now previously with x plus y, the problem was straightforward, because we know among all of these, whichever is the maximum, that will be giving you the maximum value of x plus y with the particular x. But with x or y, that is no longer true. So the problem is now, given a array of elements or a list of elements, you need to find a way to efficiently tell which one will give me the maximum XOR with a given element x. This is a very standard problem, and you can solve it using try. If you are not aware of the approach, don't worry, I will be explaining it further in the video. But the assumption is you know what a simple try is. that's it. You will be able to understand how to find out the XOR in the next part. So overall, now what we are doing, we are still doing this entire thing is still order n, but now for each L we are now doing a maximum XOR in the range. So this function, whatever the complexity of this function fx is, that will be multiplied to this time complexity as well, because previously this was just order 1, because what we know that in this list whichever comes the last, that will be the largest element, and hence we can simply do array L plus whatever is the last element in this element array and add it to array L. So that this operation was order 1 in this x plus y problem, but now in XOR y this is not just order 1, or it can be order 1, but it depends on the fact that how you are able to figure out what is the maximum possible value of the XOR with a given x from the given list of elements. So this will be the overall complexity. So let's now do a quick dry run and understand how we will actually do maximize the XOR using a try. So if you already know about it, skip the section and try to code the entire solution by yourself. As always, if you don't know about this, about how to maximize XOR using try, this section would definitely help you. So we'll do a quick dry run. We have the same array, we just sorted the array. So again we'll start with this particular L and we will try to find out all possible the maximum value of R with this L. So the approach is, we prepare a list of element for a given L, right? Remember this elements array, right? We'll prepare a list of elements for a given L, and among the list of element we just see which one will give us the maximum value with x. So now this list of element, instead of keeping it in a array, we will keep it in a try, and in try we will store the binary representation, because that will help us figuring out the XOR afterwards. We'll look at it. So for now we assume that everything can fit into 4 bits, but in reality in the original problem everything can fit in 20 bits. So whatever we are doing with 4 bits here, you have to do the same with 20 bits afterwards. So for this L, we'll start with this R. This R is definitely greater than equals to 2 and less than equals to 4. So this is a valid R. So we'll simply insert 0 0 1 0, which is the value of 2, into our try. So how to insert? Simple. Just add a new node with 0 0 and then 1 and then 0, right? So 0 0 1 0, and let's just keep maintaining a count as well, as in how many elements are there which are visiting to this node. So this is the left child, which is 0, right? And this is the right child, which is denoting 1. So this is how you will insert 0 0 1 0. Now this is also a valid R, right, for this particular L, because again less than equals to 4. So we will now insert 0 1 0 0. So 0 is there, so we'll go here again, incremented value, so that we know how many nodes are there with this particular value, or how many numbers are there which are crossing this node. 0 1. So from 1, for 1 you will go right, so you will add a new node here, right? 0 1 and then 0 0. So let's just make it here so that it is visible, and then 0 0. So 0 1 then 0 and then 0, right? And all these will be 1. Now finally this R is not a valid R for this particular L, because it is greater than 4. So this is your current set of elements which you have for this particular L. Now from this set of elements, what you want to know which one will give you the maximum XOR with X. X in this case is 2. So which one of this will give you the maximum XOR with 0 0 1 0, which is 2. So what is the definition of XOR? Definition of XOR is simply, if you have 0, like opposite gives you 0, and if same bit opposite gives you 1, 0 XOR 1 is 1, 1 XOR 0 is 1, and the same bit gives you 0, 0 XOR 0 is 0, 1 XOR 1 is 0. So if you want to maximize, you want to first maximize this bit, because you already know this value, or 2 power x, is actually greater than summation of 2 power I, where I lies between 0 and x minus 1. So even you set all the bits here, just 1 0 0 0 will be greater than all the bits set here. So that's where what you will always try is, you will always try to first set this bit. In other words, you will see if there is a number which have this particular bit set. If there is, you will always go there, right? So in this case 0, we are trying to find out number 1, so we are at root, right? Now the best choice at this stage is 1, but we don't have a 1 here, right? So if we don't have 1, only choice remains is 0, so we have to go with 0. So in other words, whatever number we have inserted so far, none of them has the first bit as 1, so we have to go with 0. We have no other choice. So the first, we want to find out the number that will be XORed with this to give us some number. So the first bit which we found was 0, which is giving you 0. Now again, your obvious choice will be to make 1 here, right? So again you will try to find out a 1. So from this, now you are at this node, sorry, so let's just get rid of this. So now you are at this node, you will again try to find out what is the best choice here. Best choice here is again 1, because if it is 1, you will get 1 here, right? So you will see if you have 1. The answer in this case is yes, you have 1. So you will go down this path and you will say, okay, I have 1 here, so you will just do 1. So notice what you are doing. If once we go down this path, we have selected all the numbers which are now starting with 0 1, right? So in this case there is just one number, but in case there are many others, this will be a complete tree, and this tree will represent all the numbers, all possible numbers which have 0 1 in their prefix. Now again 1, what you want here is 1, right? Because you are greedy, so you will try to find out a 0 here. In this case we do find out a 0, so we'll just simply use 0 here, and just the result will be 1. Now again from this case you want 1 here, so you will simply try to find out 1. So from here you want to go to 1, but there is no node, or there is no child, right child of this particular node. In other words, there is no number at all which has prefix 0 1 0, and after that there is 1. So hence you have no other choice than to go and follow 0. So you will put 0 here, and this will be your number. Now finally, once you reach the leaf node, or in other words, once you exhausted all the 4 bits, you will stop your journey, and this will be your maximum XOR. So maximum XOR for this particular x is 3. Sorry, not 3, 4 to 6. So maximum XOR with this particular x currently is 6, right? Now let's move forward. Now remember, we don't need to move R, we'll simply move our L. Now before we move L, we have to make sure that we remove the contribution of this number, right? So let's simply try to remove 0 0 1 0 from our try. So 0 0 1 0. So first we'll go 0. So let's remove the count here. We go here, we remove the count here. 0 0, so we go here, remove the count here. 1, we go here, remove the count here. and then 0. We go here and remove the count here, right? This is now the current try. In other words, this contain only the numbers in this particular range, in this L to R. Now again for this L, we'll keep on incrementing R until we can. So in this case, we'll first go here. Is this valid? Answer is yes, because you can go all the way up to 8. So 5 is valid. So now you will try to insert 0 1 0 1. So 0 1 0, and you have now 1, right? So this is what we have inserted. So let's increase everything in this path by 1, right? Now you will again do increment the R, because R can go all the way up to here, that is up to 8. So you will simply increment R and insert 0 1 0 0 1 1 0 as well. 0 1 and then again a 1 and then a 0, right? So let's just do this. This is 1, this is 0, and finally increment everything in this range. Okay. Now we'll again increment R, insert 0 1 1 0 0 1 1 0, which is this itself. So we'll simply increment the count, right? Now we'll increment R again. This time it is 0 1 1 1 0 1 1 and finally a 1. So this is your new node. So it will be 1. Increment the count, this will become 3. Increment the count, this will become 5. Increment the count, this will become 5, and finally this will become 5 as well, right? So similarly this will be the same. 0 1 1, you will be inserting 0 1 1. So I'm not inserting it, let's just skip it for now. And finally 1 0 0, you will be inserting. So let's say 1 0 0 0, which is, for the first time we have a right child of this, right, which will have 0 0 0. So let's just skip it, because it will make the tree structure a bit worse here. So let's assume that everything up till here is valid. For hypothetical situation, 8 doesn't exist at all, right? So this is your last R. Now you again want to find the same thing. This tree or this trie contains all the nodes starting from here to here, right? Now from all of them you want to find out which one will give us the maximum XOR with x, which is 4 here. So x is 0 1 0 0. We want to find a number which gives us the maximum value. Now again we want 1 here, right? The first bit to be 1. So we will look for whether there is a 1 or not. Answer is no. So from this node we have no other choice than to go to 5. Again, just to reiterate, this says that all the 5 numbers that has a prefix of 0, or all the 5 numbers that we have, none of them have a prefix that starts with 1, which is the case here. None of them starts with 1, right? So we have no other choice than to put 0 here. So this will be 0. Now again from this we want 1 here, we are greedy, so we will try to put 0 here. So let's see, does this node has child 0? Answer is yes. So we'll go here, but there is a catch. This has a value 0. In other words, there was a child somewhere before, but remember we are removing stuff as well. Now because we are removing stuff, this count now helps. Now we are saying that okay, it has node but the count is 0. It means there is no number at all which actually has the prefix 0 0. So again we don't have any choice than to go to 1, and you can verify this. All of these number that we have inserted has a prefix of 0 1 only. So we have no other choice than to put 1 here. Again this will be 0. Now we want this to be 1, so we want 1 here. So we will see the 1. The node exists and the count is also greater than 0. So this is a valid choice. So we'll simply put 1 here and this will be 1. Now finally we again want 1 here. So for 1 we want to have 1 here. So we'll see if we have a child of 1. Answer is yes, we do have a child with 1, and the count also is greater than 0. It means it does exist. So we'll simply put 1 here and this will be 1. So the maximum XOR possible with this particular x is 3, which is less than what we already have, which is 6. So we'll simply do max of 6 3, which will be coming as 6. So we'll not update anything here, and we will now try out with the next L. We'll keep on doing this until we hit or until we exhaust all the L's. Now again, before incrementing L, you have to make sure that you remove the contribution of previous L, which was 0 1 1 0. So we will simply go and remove the contribution of this. 0 1 0 0. You will remove the contribution of this. So in other words, this will become 0, this will become 1, this will become 4, this will become 4, and finally this will become 4. So this is the current structure for this particular range. Now you will simply try out whether you can increment R. If you can, you will keep on in the same fashion, you will add new elements and finally figure out which one will give you the maximum XOR with this particular x equals to 5. So hope you understand this entire solution. If you have any doubts, feel free to post them in the comment section below. If you have watched to this point, I would strongly encourage you to pause and try to code this particular solution by yourself. The overall complexity is just n into fx, where fx was, we said that whatever takes to insert, remove and query. Everything just takes number of bits, right? We are just iterating over all the bits. So the complexity is n into b, which is sufficient to pass the given time constraint. So if you have watched this point, as I was saying, try to code the entire thing by yourself. That is the most important part of this upsolving that you are trying to do, because without that you will not be able to retain the concept for a longer time, and you will not be able to understand which part you actually don't understand. Most of the time it happens that you think you understand the pieces, but when you are trying to code, you will somewhere you will see something missing, and that's where you have the time to revisit the video and see which parts you don't understand. If you have doubts, post them in the comment section. I would be happy to answer. Next, we're looking at the code. The code is straightforward. As we discussed, we just have sorted the array. After we have sorted the array, we simply go and try out all possible L starting from 0. We'll see which all is valid. For all these R which are valid, we will simply insert those numbers in our try. After this loop, we will have our try will contain only the numbers in the range L to R. So we'll simply query the max XOR with the nums of L. After this, we will simply remove the current element at position L and increment L and continue doing this. Now finally, this try has 3 functions: insert, remove, max XOR. Insert will just call insert with the maximum bit and the root of the try. Similarly, remove will do the same thing, call the remove function which is private with maximum bit and the current root, and so is max XOR. So let's look at the internal functions one by one. So insert, as we know what we were doing, we will simply increment the node value and go on in the same path as the bitwise XOR or bitwise representation of the number denotes. So we simply see if the current bit is set. If it is set, we know that we have to go to the right. In other words, we have to go to the 1 children. So we simply look at, so this node just has 2 children, 0 and 1. So we'll look at what the 1 children is. If it is a null pointer, we'll replace it with a new node and call the same function to insert the rest of the stuff starting at bit -1. Similarly, if bit is not set, we'll look at the 0 1. If it doesn't exist, we'll create a new node there and recursively insert it. Remove is also exactly same, only difference is we are doing minus minus here, and here we don't have to create new nodes because we know the node already existed because we have inserted node before. So we will simply call that particular children while doing the recursion, and we are sure that this will not be a null because of our approach. We will always insert first before removing. Now finally, max XOR, as we discussed, we will have two criteria. If the bit is set in the given number x, we will try to find a child which has a 0 value, right? So we'll look at the 0 node if it exists, and if the count is greater than 0, we will found, it means we have found some number which has the prefix of 0 at the current position. So we'll simply this will simply contribute one left shift bit. So basically this 1, if we got a 1, we know that the final result will have 1 at that particular bit, so this will contribute 2 power b to our final result. So that's where we are simply adding this to whatever we got afterwards. And if we don't have such a number at all, we have no other choice than to take the route of one child, and in that case previous value was 1, this value is 1, we know that it will be 0, so this will not contribute anything to the answer, so we just simply return whatever we got from afterwards. And the same is the case, the other case as well. So hope this entire solution makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Before going, as discussed, you can try and solve the third problem of last week's weekly contest as well. That also involves similar concept, not the bitwise XOR part, but the first part where you are given an expression, you want to optimize the complexity from order n square to something lesser. And I will see you in the next one. Thank you.